Welcome to the deep dive. If you're building any kind of serious application, you know this. The database. It's the heart of the whole thing.
It absolutely is.
It doesn't matter how clean your front-end code is or, how clever your microservices are. If that data layer starts to buckle, the whole system it grinds to a halt.
It becomes a slow, expensive mess.
Yeah.
And really, it's the highest stakes decision in modern architecture. We're not just storing data anymore.
No.
We're talking about delivering it in single-digit milliseconds and doing that reliably at a global scale. So our mission today is to cut through the noise.
Give us the blueprint.
Exactly. The blueprint for speed and resilience.
And you told me before we started, it really all begins with one question. It's not about what's trendy. It's not even about what's cheapest up front. It's about behavior.
It is all about behavior. Before you write a single line of code, you have to answer this. What is your access pattern?
What is your access pattern?
Are you doing complex data analysis? Stuff that needs these intricate, structured queries? Or are you just going for sheer, high-volume lookups that need to be instant?
And that one question immediately sends you down one of two very different paths.
It does.
On one side, you've got the structured relational world, think Amazon RDS and Aurora.
Mm-hmm.
And on the other, you have the lightning-fast key-value systems, like DynamoDB.
And we're going to go deep on both today. We'll look at how Aurora gets its performance, how DynamoDB handles massive scale, especially for writes.
And caching, right.
Oh, yeah. Why in-memory caching is your secret weapon. And then we'll finish up by solving one of the biggest headaches in serverless, that connection bottleneck problem.
Okay, let's dive in. Let's start with that fundamental choice. So You've got your data model in mind, but you need to pick the engine.
Right.
Let's say you've got a really normalized schema, customers linked to orders, which are linked to inventory. You're probably leaning relational.
Almost certainly.
So what is it about those complex queries, the joins, that makes them so hard to scale?
It's the computational cost of the join itself. I mean, relational databases are amazing for consistency, for transactional integrity. That's their superpower.
Sure.
But when you ask the engine to join, say, 5 or 6 different tables, just to build one result for a user, maybe for a personalized dashboard, that overhead adds up fast.
Every single time.
Every single time. It's CPU, it's memory, it's disk I/O, all working to stitch that data together. And for many businesses, that's just the reality. Their model is complex. So you're looking at things like Amazon RDS, or for top-tier performance, Amazon Aurora.
Okay, but then there's the complete opposite. What if I'm not running complex reports? What if I'm just running an auth service? Billions of requests, and all I need is to find a value based on a key.
Instantly.
That is the DynamoDB world right there.
Yeah.
When you're talking about massive scale lookups, a user profile, a session token, an IoT sensor status, you are built for key value.
You look up by the primary key, and that's it. That's it. Nothing else. The architecture of DynamoDB is built from the ground up to spread that data across partitions so the retrieval is always, always fast. We're talking single-digit milliseconds, whether you have 10 users or 10 million.
The goal isn't complexity. It's just raw speed and throughput.
Exactly.
So the access pattern really is the decider. But let's stay with relational for a minute. Let's say you're migrating an old system. You have to stick with SQL and transactions, but you need that hyperscale performance.
Yep. Common scenario.
Aurora is the answer. So why do people call it the performance king compared to a standard RDS database?
It's a fundamental architectural difference.
Oh.
With traditional databases like MySQL or Postgres, how do you scale?
You buy a bigger server vertically.
You buy a bigger box, exactly. You run out of I/O, you have to upgrade the entire monolithic server. Aurora completely changes this by, and this is the key, decoupling compute from storage.
Decoupling compute from storage. That sounds pretty technical.
Well,
What's the real-world impact of that?
The impact is profound for speed and for recovery. First, the database engine, your compute layer, it doesn't have to manage writing to disk and replicating data anymore.
It's offloaded.
It's completely offloaded to a purpose-built storage service. That means way less I/O overhead on your database instance, which translates directly to faster queries.
Okay, and the second part, the resilience.
Right. Resilience is baked in. The storage layer automatically replicates your data 6 times across 3 different availability zones. And this isn't just a backup plan. It's actually a performance feature.
How is that a performance feature? Doesn't replication usually add latency?
That's the brilliant part. Because the storage is shared and managed by the service, failover is incredibly fast. We're talking under 30 seconds, often.
Yeah.
If your primary compute instance fails, a replica can take over immediately without having to copy or sync huge amounts of data. The data is already there, consistent and shared. You maintain performance right through a failure.
Which is pretty much impossible with a traditional architecture.
It is. Now, that abstracted storage layer, it does mean you give up some fine-grained control that a traditional DBA might be used to.
Like it's a trade-off.
It is a controlled trade-off. You trade low-level tweaking for a system that just handles massive scaling and self-healing for you. For most modern apps, that's a trade you make all day long.
Let's talk about scaling reads. It's Black Friday. I'm running a huge e-commerce site, and thousands of people are all looking at the same product page. That's a classic read-intensive workload.
A huge one. And you can't let millions of reads hit your primary database while it's also trying to process orders, the writes. You'll create a bottleneck.
So you use read replicas.
Exactly. And with Aurora, you can spin up to 15 of them. And because of that decoupled storage we just talked about, the replication lag between the primary writer and those replicas is tiny, often just tens of milliseconds.
So you could just spread the traffic out across all those replicas and keep everything feeling snappy for the user.
You got it. You protect the core transactional engine.
Okay, so we've handled complex queries. But sometimes it's not complexity that's the problem. It's just raw, insane volume. What about apps that are all about massive writes?
Now we're back in the DynamoDB world. And we're talking about the challenge of scaling writes.
So things like a live gaming leaderboard.
A perfect example. Player scores changing every second. Or an IoT fleet dumping sensor data every few milliseconds. To scale writes like that in a key value store, you have to understand a concept called capacity units.
Right, capacity units. That's the currency of DynamoDB. If you're used to thinking in terms of provisioned IOPS on a traditional database, how should you think about these RCUs and WCUs?
It's a philosophical shift. When you buy a provisioned IOPS for an RDS instance, you're buying a throughput ceiling that's tied to the underlying hardware. With DynamoDB, capacity units are more like a contract with AWS. You're defining the exact throughput you require.
So what does one write capacity unit, a WCU, actually get me?
One WCU gets you one successful write per second for an item up to 1 kilobyte in size. If your item is bigger, say 3 KB, that single write will consume 3 WCUs.
And it's the same idea for reads with RCUs.
It is. And the key is, if you don't provision enough capacity for a massive flash sale, your requests will start to get throttled. They'll fail.
That sounds like a lot of pressure for capacity planning, especially with spiky, unpredictable traffic. Is there a way around that?
Absolutely. For new projects, or if you just hate capacity planning, you use DynamoDB on demand. It used to be called serverless. It just completely eliminates the need to manage WCUs and RCUs yourself.
So the database just scales up or down automatically based on the traffic.
Instantly. It's fantastic for those chaotic workloads. The trade-off is usually a slightly higher cost for that convenience, but it guarantees your performance won't suffer during a spike.
Okay, so we've scaled the database itself, but you mentioned shaving off milliseconds. What happens when even Aurora's fast replicas or DynamoDB's speed aren't enough? We're talking microseconds now.
Now you bring in the ultimate speed layer, in-memory caching with Amazon Elasticache.
And the goal here is pretty radical.
The goal is to bypass the database completely. If the data hasn't changed in the last minute, why are we hitting the database for it at all?
Right. A travel site with flight prices that only update every 5 minutes. You just cache the results.
Precisely. You cache product info, session data, frequently requested query results. Getting data from memory is an order of magnitude faster than even the fastest disk. It takes a massive load off your database.
But caching adds complexity, right? You gain speed, but now you risk serving stale data.
That's the core challenge, cache invalidation. Usually, you rely on a TTL, a time to live. You set a lifespan for the data in the cache. When it expires, the next request pulls fresh data from the database and updates the cache.
And Elasticache gives you 2 main engines for this, Redis and Memcached. How do you choose?
It really comes down to your data structure needs. If you need complex data types like sorted sets for leaderboards, or if you need high availability features within the cache itself, you choose Redis.
Redis is the feature-rich one.
It is. If your needs are simpler, just pure key value lookups for maximum speed, like caching HTML fragments, then Memcached is often the better choice. It's leaner, simpler, and built for raw speed.
That's a clear breakdown. Okay, let's switch gears to a really painful real-world problem, especially with serverless. the connection problem.
Ugh, the headache of database noise.
Yeah, so you launch a new feature, and suddenly thousands of Lambda functions spin up all at once. Each one tries to open a new connection to your RDS database.
And those traditional relational databases were just never designed for thousands of connection handshakes every second.
So even if your database has plenty of CPU and memory, it can just fall over.
Yeah.
Because it's spending all its time managing new connections instead of actually running queries.
It's a classic problem. And the architectural fix, the required solution for modern serverless, is Amazon RDS Proxy.
A middle layer.
Exactly. It's an invaluable middle layer that sits between your application and the database. Instead of all those functions hitting the database directly, the proxy pulls the connections.
So the proxy holds a small, stable set of connections open to the database, and the Lambda functions talk to the proxy.
That's it. A function connects to the proxy, which is super fast, and the proxy routes the query through one of its warm, persistent connections. It completely shields the database from that connection storm.
It protects the engine.
It protects the engine and ensures you have smooth performance, even during those massive traffic spikes.
Okay, that solves the local stress test. But what about the ultimate one? Distance. You can't beat the speed of light. If my database is in Virginia, my users in Singapore are going to feel that latency.
And this is where global databases become part of the performance strategy. You have to solve the physics problem. You need to get the data geographically closer to your users.
How does that work in practice?
Well, in the non-relational world, you have DynamoDB global tables. They are fully managed, multi-region, and critically multi-active.
Multi-active, so I can write in London.
And a user in Tokyo can read that write almost instantly. And they can also write to their local Tokyo endpoint. It allows users to read and write to the closest geographical point, which just slashes latency.
And for relational, you have Aurora Global Database.
Same idea. A primary region with up to 5 read-only secondary regions with incredibly fast replication. The point here isn't just disaster recovery anymore. It's about actively designing your architecture to minimize network distance for every user.
Okay, let's bring this all together. We've gone through a bunch of tools. Can you give us the quick reference guide?
Sure. The blueprint is this. First, always start with your access pattern.
Right.
If you need complex queries but also high performance, you use Amazon Aurora. You lean on that decoupled architecture. If it's massive scale with simple key value lookups,
DynamoDB.
DynamoDB is your tool. You focus on the capacity units to guarantee your throughput.
What about scaling a read-heavy app?
You start with read replicas to spread the load. Then you layer Elasticache on top for that microsecond speed, but you have to be careful with your cache invalidation strategy.
And finally, for serverless.
If you're using serverless or microservices with a relational database, you must use RDS Proxy, period. It's not optional. It protects your database engine from connection noise.
So the big insight is you have to match the specialized tool to the job. It's about understanding if your bottleneck is complexity, capacity, raw speed, or connection management.
That's it. We are long past the days of the one-size-fits-all database server. Modern architecture is all about specialization.
Okay, so before we wrap up, a final thought for our listeners to take away.
I'll leave you with this. We've talked about how Aurora decouples compute and storage, and how DynamoDB offers serverless capacity. So think about this. How do these modern architectures completely challenge our old assumptions about capacity planning?
The assumptions that were all based on scaling a single monolithic server.
Exactly. When you can scale compute and storage independently, and when you can pay for pure throughput, how does that fundamentally change your approach to cost, to optimization, and even to how you design your application in the first place?
A great point. If the server isn't the bottleneck anymore, what is? That's the architectural challenge for you to explore. Thanks for joining us on this deep dive. We hope you're better equipped to tackle your next big performance challenge.